Yeah. Is my screen visible to you?
Yes, sir. Yes, sir.
Okay. All right. So last time we discussed about milli machines and Moore machines. So very simply speaking, for milli machines, the output of the machine depends on both the present state and the input. For Moore machines, the output depends only on the present state. It doesn't depend on the input. Alright. Now, uh, what we also discussed is central to the operation of this finite state machines is is a storage device. Fundamental to the and the simplest one is a D flip-flop, and its operation is very simple. Present state, whatever be the present state, your input. So whatever be your present, sorry, this is your present state and this is actually the next state. So whatever be your input present state, if you have a if your input is 0, your next state is 0. If your input is 1, the next state is 1. This is the behavior of the D flip-flop. Okay, this is the behavior of the D flip-flop. Whatever be your present state, if the input is 0, the next state is 0 if the input is 1. So it is, often represented like this. Of course, if you are talking about so this is your input and this is your output. This is your D. This is your D flip-flop. All right, and this is the. So let us look at the circuitry of a D flip-flop. So you see that there are actually two parts here. Okay. There are two parts here, and both the parts are quite similar. So if you look at this part here, so what do you understand of the behavior, I think. Uh, so what do you understand of the behavior here? So let us say that you have, I'm just redrawing the circuit. That's all. Okay, so this is your circuit. So how does the circuit behave? Suppose the output here, yeah, sorry, someone is saying something. Hello? Okay. So let us say that you have a 0 over here. Okay. Let us say that you got a 0 over here. Okay. So suppose this is 0. So it also means that you got a 0 over here, right? And that means that you got a 1 over here. So let us say that you got, 1 here and 1 here because this is a floating. Okay, so now you got a 1 here and you got a 1 here. So, okay, so here as you can see, this is going to, feed over here. So you got a 1 over here and the output is again 0. So what you can see that, and this is a symmetric circuit, so you could just do the same thing. You could analyze it the same way. If you had a 0 here, this you would have a 0 here, and then you would have a 1 here and a 1 here. Okay, so you have a 1 here and so on. So, and that would give you a 0. So this is symmetric. So what you see is that data gets latched in. So this is a cross-coupled. Cross-coupled NAND gate. Alright. So here the data gets latched, and the requirement for the data to get latched is that you should have a 1 here and a 1 here. Alright. You should have a 1 here and a 1 here. Now, consider the situation that you have a 1 here and a 0 here. Okay. Consider the situation that you have a 1 here and a 0 here. So again, let us consider the situation that suppose you had a 0 here. All right. Suppose you had a 0 here. So this 0, will lead to a 1 here. Okay. Suppose you had a 0 here. So this 0 will, whenever you have an input 0, so the output is 1, and 1 and 1, the output is 0. All right. 1 and 1, the output is 0. So it gives the same input. And you consider the other situation. Suppose you have, so let us see. So if you have a 0 here, so let us see. If you have a 0 here, then this 0, gives as a result you have a 0 here, and then you have a 1 here, and again you have a 1 here, and the result is a 0. So this 0 is retained. Now let us consider the other situation. You have a 1 here. So let us, or maybe I can just lower this 0 and write it. Right 0 here. Now let us see that. So suppose you have a 1 here. All right. You have a 1 here, and again, as before, let us say, not that, you have a, let's say that you have a 0 here. You apply a 0 here, and you have a 0 here as before. Okay. So now that you have applied it, so it is, it is 0 here and a 1 here. Okay. It is 0 here and a 1 here. Earlier we considered 1 and 0. Now we are considering 0 and 1. So you had a 0 here, apply a 1 here, and suppose its earlier state was 0 as before. So now this 0 forces this output to go from 0 to 1. All right. So it goes from 0 to 1, and well, so this was also 0, so here also you have a 0 to 1 transition, all right, and then you have 1, 1. So of course, if this was 0 here, presumably you had a 1 here, so this one goes from 1 to 0. So this is a very important, case. That is, if you have a 1 here, if you have a 0 here and a 0 here, this 0 forces a change of state. It forces the 0 to become 1. Okay, it forces the 0 to become 1, and then it latches 1. All right. So as you can see here, these inputs. So important thing is you have X here and X bar here. Okay, that is what is important. So if you have, for latching, new data, what you do is you have X here and X bar here. That is important. So it's always complementary. It's either 1, 0 or 0, 1. So in that case, you find that the output is also, it follows the input. Now, this is what you've seen here. I mean, but you see that here you have an extra, you have an extra circuitry. So let us just redraw that and see how it works out. So you have this as before. As the output. So this one is getting in here, and actually don't need this part. And here we are putting these two gates. And here, let us say that we apply the clock. So you have already seen the operation of this gate. So when the clock is 0, the output, so stays latched. All right. And if the clock is 1, okay, then as you can see, if you have a 0 here, so we are applying X and X bar, okay, we're applying X and X bar. So if you have 0 here, you go to 1 here, and what you have is 1 and 0, right? On the other hand, if you have, let us say, so it is symmetric, of course. So if you apply a 1 here and a 0 here, if you apply a 1 here and a 0 here, then the output is that you get a 0 here and a 1 here. So as you can see, whatever data you apply here, because you saw that the complementary item is going from 1 you're getting 0, and from 0 you're getting 1. All right, or maybe if you like to do it like this. From 1, from 1 you are getting 0, and here from 0 you are getting 1. So now what you see is that, so so now in this case you see that from 1 you will get 1, right? From 1 and 0, that is what you will get. From 1 and 0, this is what you get. And from 0 and 1, this is what you get. All right. This is what you get. So that gives you the essence. So we, as you can see, because of this behavior, I mean, this is the essential aspect. So here, as you can see, you have x 0, 1. So irrespective of what you get here, this is the present state. Sorry. This is the present state and this is the next state. So irrespective of what you have in a present state, the next state follows the input. Okay, it follows the input. So that is the basic behavior of the D latch. Now here, what you see is that you have this one. So you have got this is called the master. Well, let me write it below. And this is, so you have got 2 D units, and what happens is, so as you can see, the transfer happens when the clock is 1. Okay, the transfer happens when the clock is 1. Okay, so this is enabled. When the clock is 0, the no transfer happens. It doesn't react to the input. Okay, so this flip-flop, it reacts to the input only when the clock is 1. When the clock is 0, it doesn't react. So here the way it works is that when the clock is 1, the data moves from the input of the master to the input of the slave and stays here, because when this is 1, this is 0. All right. So it stays here, and then when it goes from 1 to 0, this one will go from 0 to 1, and so basically what is happening here is x, let me put it this way. So here, x comes here when the clock is 1, and when the clock goes from 1 to 0, this gets transferred here. All right. So it's so the data doesn't go straight from the input to the output. It stays blocked over here until there is a transition of the clock from 1 to 0. Okay, that's why it's called a negative edge trigger, because data goes, so this is a negative edge. 1 to 0, this is a negative edge. All right, so this is how this flip-flop basically works. It's a negative edge triggered D flip-flop. Now, it also has two inputs, as you can see. This is preset bar and clear bar. Actually, that bar is not visible now, so let me just wipe it out. You can see the bar. So it is preset and clear. These are, so what you can see is that when the preset is low, okay, if you make the preset low, so okay, so when the preset so this is preset bar and clear bar. So in that case you could say that when the preset bar is low, okay, when the preset bar is low, in other words, when preset is high, so when preset bar is low, this output is DM is forced to 1, right? And DM is forced to become 1. And so it is forced to become 1. And when it is forced to become 1, so we assume that only one of these are forced. So either you make preset bar 0 or you make clear bar 0. So let me put it this way, that clear bar is equal to 1. All right. So preset is 0. So clear bar doesn't have any effect because it is forced to 1. And then what you see is that so this is 0. Okay, so this is forced to 1, and So you'd expect, okay, when this is forced to 1, so you have a 1 here, and if your clock is 0, then what you find is that um, this is 1, so 1 and 1, the output is 0. So this preset bar, when you make it 0, it forces the output to 1. Similarly, when clear bar is forced to 0, the output becomes 0. So during normal operation, this preset and clear lines are meant to be kept low. Okay, so preset clear equal to 0 for normal operation. All right, so this is synchronous because the transfer happens only when the input is it's clocked. Over here, on the other hand, you find that the preset and clear are connected to both the master and the slave. So this will force the output to become 1 or 0 at any time. So that is the behavior of this preset and clear lines. So this is the basic behavior of a D flip-flop, which is the the storage circuit which is used. Okay, now let us look at some examples of Mealy machines. So let us see if we can design a Mealy machine to perform 2's complementation of a given input. So let us just consider some arbitrary string. So let us say 0 1 1 0 0 1 0 0. So this is an arbitrary string. So can you work out in your books, in your notebooks, how you will do this? So how do we do the complementation? So first we complement. So when you complement, this one will become, and then you increment. We are taking the 2's complement. So you increment. So this will become a 0, this one will become a 0, this will, yeah, this will become a 1. And then these remain unchanged. So if you look at it, there is a very interesting pattern. All right. So you have the string, you have, so the leading zeros, what do you observe? bits are complemented, isn't it? So as you can see, these remain the same and the subsequent bits are complemented. Alright, so can you design the machine? You know how to design finite state machines, right? So can you design the finite state machine for, say, you already know how the machine behaves, all right? So can you design the finite state machine to perform 2's complement? Yeah, are you with me?
Yes, sir.
So why don't you just do it in your notebooks? Why don't you do it in your notebooks and someone can just, I think you can post it here, right? So one of you can just post it here also. Just try. Yeah, you should. It's a very simple machine. Just try to. So the input alphabet is 0, 1. The output alphabet is also 0, 1, as you can see. So just, how many states should you have, first of all? How many states should this machine have? Can you tell me? Yeah?
3, sir.
Why do you say 3? Can you justify?
So why you need to keep track as long as you are reading zeros, then your state change when it reads a 1 and another
No,
state change for all
no.
subsequent.
Can't you have 2 states? Let me call this S0.
You might be able to collapse it. I haven't tried it.
This
Just
is S0, this is S0, this is S1. Alright? To the right of this is the S0 is also the initial state.
okay, yeah, fine. The first time we read a 1, we just change the state.
Right.
Yeah.
So just see if you can design the machine this way. So you can just design it and you can post it. So where will I see the post? Yeah, can someone just? It's a very simple machine. So can someone?
Yes, I'm doing it. Just a second.
Okay, that seems good enough. So yeah, that looks fine. So let me see what I've got. So yeah, you have got 2 states, all right? You have got 2 states, and this is, yeah. So So as you can see, you start with, this is your start state, and on zeros. So as long as you get, these are your leading zeros. As long as you get zeros, you output 0. Once you get a 1, you output 1, but on that you also make a transition to this state. And then it is all complementation. If you get a 1, you output 0. If it is 0, you output 1. All right. So this is straightforward. Now, can you, so your, the design of the machine is fine. So now, can you, write down the, so as we discussed last time, you need to have two functions, or one is the next state function, and the other is the output function, right? So for the machine you just designed, can you write down the next state function and the output function? So this one, as you know that both for a Mealy machine, both these functions depend on the input and the present state, right? Or either way, you can also write it the other way. Maybe it will be easier for you to think this is, they depend on the present state and the input. All right. So this is your state transition function, and this is your output function. I think that is denoted by lambda. So you need to, write down. So from the diagram that you got, can you write down these two functions? So again, maybe one of you can just post, write down this function and post it here. Next state and the output function. Yeah, can you do that? I mean, these functions are also very simple for this machine. So how many input variables are there for these functions? How many input variables?
Sir, 1.
Why 1? It's over here, whatever I written, it depends on the present state and on the input, right?
Oh,
So
so you mean the total input or the external input? Total input will be 1 for the state and 1 for the bit being read.
Yeah, so present state and input. So this input is for the system input. That is the primary input, you can say. And present state is actually the secondary. Yeah, present state is the secondary input. So if you want to relate it to the Huffman model, so let me just write down. This is your, if you want to relate it to the Huffman model, this is your primary input and this is your so how many bits for the present state and how many bits for the input for this particular machine?
So
How many?
present state 1 and input is 1.
So so you have 2 bits, right? This function has 2 bits as input. So yeah, so I've not yet seen anyone posting it. Has anyone? Yeah, okay, someone has posted. So let us look at this. Yeah. So if you're in the present state for a 1, yeah, that's all right. So this is fine. And um, the output function, if you have a 0, if you have a 1, yeah, so that is fine. So I hope all of you are okay with this. So here he has written it this way. This is fine, but it's a little more convenient to write it in this form. This is the usual form. It's the same actually. So maybe I can just put it here. So it is really the same as this, but this is the way it is usually written. All right. So you have the present state, uh, and okay, I mean this has been written, but really, what we are saying is that this is the input, and present state is here. All right. So this is your present state. This is your so it is so if the present state is Q0, so on input 0 it remains in the present state. On input 1 it goes to that other state. Output is 0. So this is the tabular representation of these two functions. Okay, so this is how it is usually represented. All right. Now note that here the state is symbolic. Okay, the state is symbolic, but when you want to implement it, you'll have to encode it. So these are possible encodings. So you can encode Q0 with a 1 and Q1 with 0. So that is one way of encoding it. And then you can, so this is the same table, but here we don't have Q0 and Q1 as symbolic states. Here these states have been encoded. All right. So now you actually have, a Boolean function that you can realize. All right. You can realize that. So we have come to the end of the class. So in the next class, so we'll actually, so you need to realize these functions with D flip-flop. So try realizing this function. You can just take it as a very simple exercise. So try realizing this table. So there are two functions here really. One is the next state function and the other is the output function. So this could have been written as delta and lambda also, but anyway, it's written like this. So you can just try to implement this using flip flops and other gates. All right, I think we'll stop here today. Okay, thank you.